Good afternoon, dear students. Today we will continue talking about the derivatization of silica. Now, we said that silica can be derivatized according to its silanol group. So once we have silanol, due to the acidity of silanol, we can get silanol derivatized via hydrocarbon. Now, hydrocarbon like C8 or C18. Okay, C18 sometimes called ODS. The reason of this name related to the IUPAC name of C18. C18 is octadecane, so octadecylsilane, octadecylsilane ODS. So sometimes we call C18 ODS. So if we want to derivatize silanol, we have to have a head of silicon here containing a halogen. Now, by removing HCl, we can obtain, in this case, covalent bond formation between silicon atom and oxygen atom. And this chemical derivatization is quite stable, and it is the reason behind the stability, robustness of reversed phase columns such as C18 column. Now, one of the drawbacks of this derivatization that silica itself, it usually has small particles, and these particles of silica is quite complex, and it has pores, and these porous particles make some of the silanols inaccessible for hydrocarbons. So it's more or less impossible to get all these silanols derivatized in silica due to the complexity nature and porosity of the silica particles, and also due to the bulkiness of hydrocarbons. You know that steric hindrance, if you have here three silanols, okay, three silanol groups, you can't get all hydrocarbons accessing these groups. The steric hindrance of hydrocarbons prohibits a new hydrocarbons to be immersed between these two large groups. So due to the bulkiness of hydrocarbons and the complexity of silica particles, we cannot guarantee complete derivatization of silanols. Now, silanols are hydrophilic. Okay, so this hydrophilicity will make undesirable interaction with analytes, and if we cannot control the hydrophilicity of silanols, they will be a source of troubles for us. So silanols not necessary to be reactive, okay, unless we have silanols as free form. I mean, this kind of silanol is quite reactive and it is quite hydrophilic. So this kind of silanols, we call it free silanol, and it is a source of troubles for us. Now we have other source of underivatized silanols, but they are not a major source of troubles. Now, one of these forms of silanol, two silanols at the same silicon atom, we call this kind of silanol geminal silanol. Geminal, when you have two functionality in the same atom. If you have two functionalities in the same atom, we call it, in organic chemistry, we call it geminal. So we have geminal silanol. Now, geminal silanol are not quite reactive, and the reason behind that, the oxygen and hydrogen, they are interact via hydrogen bonding. So the molecule is busy with itself. It is, in other words, not quite reactive to be a source for troubles during the analysis. So geminal silanols are not reactive enough So we can deal with them without any trouble. And also we have vicinal silanols. Now vicinal silanols, when we have two silanols at different silicon atom, but they are in neighborhood. So we have these silanols in neighborhood, but they are in different silicon atom. Now again, these can form a mutual hydrogen bonding, and this hydrogen bonding will reduce the reactivity of the overall groups. We call this kind of silanols vicinal silanol. So just to recap what we mentioned so far, that vicinal and geminal silanols are not quite reactive, so we can deal with them without any sort of trouble. Whereas free silanols is very reactive, it is acidic, hydrophilic, polar, so it's a trouble, particularly with basic groups. Why basic analytes or basic groups? Now, let's imagine that we have basic drug. Now we have drug, okay? For example, like naphthalene derivative with amino group. Now amino group, if you have a spacer here, amine will be basic. Okay, it is not directly attached with the benzoid structure of the analyte. Now, if we have hydrocarbons in C18 column or ODS column, as we said, and we have a free silanols. Now, the majority of the drug will make with mobile phase partitioning. So, if we have mobile phase here, we have liquid stationary phase. So we end up with what? With the analyte, we end up with partitioning. So we don't have any problem with the hydrocarbons, but minority of the population of this analyte will interact with silanols. Now silanols in a neutral pH, it will be what? Ionized. It is acidic, has a pK around 4. So in pH 7, it will be completely ionized. So silanol will be ionized. I mean free silanol. Now, the same thing that the basic groups of analyte will be also ionized at neutral pH. So this ionization will enhance what? Will enhance salt formation between the ammonium head of the analyte with the oxide head of silanol. So part of the population of this drug will interact analyte with positive group. So we have what? We have salt formation. Now this or these groups of these molecules of analyte will be late in terms of elution in comparison with the majority of analytes. So from the same type of analyte, when you have elution, I mean when we remove the analyte from the column, the population will go almost together. Okay, but due to this minority of analytes, they will be late in comparison with the majority of analyte. So there will be a source of what? Of tailing. The peak, instead of being sharp like this is the ideal one, it will be a peak with tailing. And this tailing due to what? Due to this kind of analytes. They have not only partitioning, but also they have what? They have salt formation with the stationary phase. So they will elute later than the majority of the analytes. Now, this source of tailing is nasty, and the reason of this, that when once we have tailing, then you cannot get two compounds separated perfectly. So they will be overlapped. So overlapping will make the analytes badly separated. So all the time, the main target for us to gain sharp peaks and identical elution of analytes. But tailing, as we see here, that it is a source of overlapping and bad separation will be resulted. So, how can we solve the tailing effect of silanols? Now, silanols might affect other kind of compounds, but not with the same severity of basic compounds. Unfortunately, the majority of drugs are basic. So we all the time complain of bad separation for basic compounds in reverse phase columns. And the reason behind this kind of separation is the tailing effect, and tailing is resulted from free silanols which cannot be derivatized by hydrocarbons. Now, because we cannot derivatize these silanols, these free silanols, we have some strategies by which we can manipulate this kind of problem. One of the strategies is blocking the reactivity of silanols by small entity. If you remember that hydrocarbons cannot access some of the silanols due to the bulkness of other alkyl groups. But if we add very small entity, we can get this kind of silanol derivatized. An example of these entities is TMS. TMS, you have silicon, methyl, 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 and chlor, or brom. Okay. Now, the same reaction will be occurred with silanols. Okay, but here that we don't have a hydrocarbon chain, so this is a small compound. So it just this small compound will come here. Okay, HCl will be removed, and then covalent bond formation will be happened between silicon atom and oxygen silicon atom of TMS and oxygen atom of silanol. Okay. Sorry for this. We call this procedure end capping. End capping. So we capped the free silanol group here by what? By this small group. Now, do we are we obliged to do end capping by ourselves as operators or as analysts? The answer no. That we just purchase this kind of columns and entitled with end capped columns CAT. So end capped column is suitable for basic compounds. Now we have also other strategies to deal with derivatization, or to deal with free silanols. In addition to the derivatization, we will mention them later on if God willing.